Hi guys. Okay, so let's look at the homework questions from chapter 6 that relate to Lewis structures. So first of all, this homework question number 53, which is talking about asking to calculate the total number of valence electrons. So how do we do that? So I've picked in two. One is the carbon tetrachloride and the other is the hydroxide ion. So for carbon tetrachloride, so first of all, you need to look at individual atoms. So you should be able to recognize that this is made up of two atoms. One is carbon and the other is chlorine. So there is one carbon and there are four chlorines. Okay, so one thing is that. Next is you're going to look at the number of valence electrons. So total, so in order to get the total number of valence electrons, you're going to look at the individual valence electrons. Now carbon belongs to group 4A. Okay, so carbon is in group 4A. And group 4A means that there are four valence electrons. And chlorine belongs to group 7A, and 7A means there are seven valence electrons. Okay, so four coming from carbon, and seven electrons coming from chlorine. But there are four chlorines, so we have 7 4s are 28 electrons coming from chlorine and 4 electrons coming from carbon, 4 times 1. So this becomes 32. So a total number of 32 electrons are present, is that total valence electrons in carbon tetrachloride. Okay. Next, OH 1 negative. Now this means there is 1 electron extra. If there were 2 negative charges, it would have been 2 more electrons. Okay. So oxygen is in group 6A, okay, and hydrogen is in group 1A. So oxygen has 6 valence electrons and hydrogen has 1 valence electron. And there are 6 valence electrons are coming from oxygen and 1 coming from hydrogen, and then there is plus 1 more electron. Okay, that's the coming from the charge. So now a total of 6 plus 1 plus 1. So we are looking at 8, total number of 8 valence electrons. Okay, so that's one piece. Next is draw the Lewis structure of this molecule, which is sulfur difluoride. So here we are going to look at sulfur. Let's calculate the total number of valence electrons first. So let me write this down. So the first step is total valence electrons. Okay, so sulfur, there's one sulfur and there are 2 fluorines. Each sulfur is bringing 6 electrons because sulfur is coming from 6A. So there are 6 valence electrons. Fluorine is coming from, or fluorine belongs to 7A. So there are 7 valence electrons, but there are 2 fluorines. Okay, so we are going to get 6 electrons from sulfur, and we have 7 2s are 14 electrons coming from fluorine. So a total of 20 electrons. Okay, so now we have to place these 20 electrons. So our first was this step. Now the second step is identify the central atom. So the central atom is, what is the central atom? The central atom is based on, one second, central. Okay, so the central atom is based on, number 1, lowers, but not all the time. So it's anyways, lower electronegativity. That's one piece. And the second thing is the capability to make the maximum number of bonds. Okay. Now, lower electronegativity and maximum number of bonds. So if you see the trends in the periodic table, fluorine has a higher electronegativity than sulfur. So this is one piece. Okay. So as we move in the periodic table from left to right, in the same period, or even if, in general, the left to right, when we move, we see that the electronegativity increases. So fluorine is the highly electronegative element, okay? Maximum number of bonds. So fluorine can make only one bond, but sulfur can make 2, 4, and 6 bonds. Okay, so this is based on the number of bonds. So let's look at the handout. I want to show you that so that you can refer to that for other elements also. So hang in there for a minute. Okay, so now look at the handout. Now here you will see, I have put all these tables. So as you can see here, in this handout, you can see these are the valence electrons, and this is shown in the electronic configuration, which is a good thing. Okay, so as you can see, all of the group 1As, we see the pattern. It's 1s1, 2s1, 3s1, 4s1. So s1 by default, that is the valence electron. So this will only make one bond. Group 2A is 2s2, 3s2, 4s2. So because of the s2, the valence electrons are 2. Now comes the group 3A, the p block side. So here you see it is the 2s2 and p1. So a total of 3 valence electrons. Similarly here, aluminum, 3s2, 3p1, 3 valence electrons. Gallium, 4s2, 4p1. So these are the 3 valence electrons. Now look at carbon. Carbon is 2s2, 2p2. So 4 valence electrons. Silicon, 3s2, 3p2, 4 valence electrons. Germanium, 4s2, 4p2, 4 valence electrons. So you get a picture? Now look at 5. 5a. 5a is nitrogen, 2s2 and 2p3. So 2 from S and 3 from P together make 5 valence electrons, okay? So phosphorus is also same thing, 3s2 and 3p3. So this 2 plus 3 is 5 valence electrons, okay? And similarly with oxygen. Oxygen is in group 6A. So the total valence electrons are S2, S2, and 2p4. So 2 plus 4. Next is S2 and p4. In sulfur is 3s2 and 3p4. So that's 6 valence electrons, okay? And so forth. Next is the group 7A. So that is S2 and p5. So 2s2, 2p5 is fluorine, 3s2, 3p5 is chlorine, and so forth, okay? And then comes all the noble gases, which have fully filled orbitals. NS2, like any neon is 2s2 and 2p6, 3s2 and 3p6, 4s2 and 4p6, and so forth, okay? So these are, and helium is just 2s2. So these are the valence electrons. And depending upon the valence electrons, we have the number of dots. So that was the hydrogen, right? In group 1A, it can only make one bond. So the red color you see are the usual number of bonds, but the ones that are given in parentheses are the bonds that are made in different conditions, different situations. Now, normal conditions would mean that when each of these elements, when they combine, or these atoms, when they combine with another atom, and that other atom is lower in electronegativity, then they are going to make their normal number of bonds, which means carbon will make 4, silicon will make 4, nitrogen will make 3, oxygen will make 2, fluorine will make 1, right? And noble gases will not make any bonds. Similarly, phosphorus will make 3, sulfur will make 2, chlorine, bromine, iodine will make 1. So these guys are like, these are like when they're connected with some lower electronegativity atom. But if they combine with oxygen, then phosphorus can make 5 bonds. Sulfur can make 4 and 6 bonds. See this? Phosphorus can make 5 bonds. Sulfur can make 4 and 6 bonds. See that? Then chlorine, bromine, iodine. Actually, chlorine can make 3, 5, and 7 bonds. And bromine, again, 3, 5, and 7 bonds. And iodine also 3, 5, and 7 bonds. Because they have d orbitals, which are just lying vacant. And so because of that, that space is available to them. Okay. Now, interestingly, xenon, if you look, all the noble gases, they are not making any bonds, but you can create experimental conditions in which, atoms are forced to, make bonds. So you make bonds, basically what is bond formation? It's just pairing of electrons. Okay. So if there is space available to pair the electrons, why not? So these guys have d orbitals with them. So that's vacant. So they can use them, okay, for pairing. And you will study about this. It's all about hybridization, so xenon can make 2, 4, and 6 bonds. Okay, so just keep this handy with you. Once you start making the Lewis structures, you can refer to this. So this is one piece. Next thing that you're going to look at is the electronegativity, the one that we've been talking about. Electronegativity. Now look at the electronegativity values. So there is an electronegativity increases in the periodic table when you move from left to right. In other words, all the non-metal side, the electronegativity is going to be higher. Metallic side, the electronegativity is lower. When you move down, top down in the periodic table, the electronegativity decreases. And what is electronegativity? Electronegativity is love for electrons, ability to attract electrons. So you see here in all these, you see 4.0 is the highest. All of these, just look at them. 4.0, that is a fluorine, is the highest. So it is on a scale from 0 to 4.0, the highest being 4. So that's for fluorine, which means that fluorine is going to attract the electrons with the greatest force. But as you move down, chlorine, bromine, and iodine. Iodine has lower electronegativity than bromine. Bromine has lower than chlorine. Chlorine is lower than fluorine. Okay, so top down, the electronegativity decreases. Okay, so same is the case. You see cesium is very low, and so all the metals have very low. And then now if you see carbon, nitrogen, oxygen, fluorine, carbon is 2.5, nitrogen 3.0, oxygen is, so in other words, nitrogen is less electronegative than oxygen. Nitrogen is 3.0, oxygen is 3.5. So nitrogen is 3.0 is lower than, like, less capability or less power to attract the electrons. Okay, so that's the deal with these, the values. Now, based on these values, there are 3 types of bonds. One is the electronegativity difference in the bonds. When we look at the electronegativity difference, that is the difference in the bonds. If it is from 0 to 0.4, then the bond is non-polar, which means that the electrons are shared equally. As you can see, equal sharing of electrons. Next is when the polar bonds means that the electrons are shared unequally. So that means that the electrons are spending more time in one side than the other. Okay, this means that the electrons are spending more times with more electronegative atom than the other. As a result, a polarity, a dipole, is induced in a molecule. One side is slightly more negative than the other. So this charge means delta negative, and the other charge is delta positive. Okay, the side where there are more electrons, that is delta negative. The side which is less electrons, they're spending less electrons, is, in other words, the electron that is more electronegative will pull the electron clouds towards itself. So in that case, we will see that the delta negative charge appears. A more electronegative atom will always pull the electron clouds towards itself, and it gives a delta negative charge. Delta positive charge is on the side where which is less electronegative atom, means it doesn't love electrons. So it's unequal sharing of electrons. Okay, but when the electrons are completely transferred, there is separation of charge. In that case, we see ions are formed, and that happens when the difference in electronegativity is between 1.8 to 3.3 and higher. Okay, so that's the deal with the electronegativity, and based on that, there is an overall polarity in the molecule. Now, polarity is when the dipole is induced. Here you see oxygen is more electronegative than carbon. Okay, oxygen is more electronegative than carbon. So what is happening then? Oxygen pulls the electron clouds towards itself. The other oxygen also pulls the electron clouds itself because of the nature of oxygen. So what is happening now? That the equal sharing is happening. So even though oxygen being highly electronegative is present in this molecule, but the overall pull, the effect is cancelled out. So it becomes a non-polar molecule. Okay, so individual bond, oxygen and carbon bond, individual bond is a polar bond. That is why the see the arrow pointing towards oxygen. Oxygen is the one that has induced the dipole because it has pulled the electron clouds towards itself. But with the equal same force on the opposite side, the other oxygen is also pulling. So it's like a tug of war. So the effect cancels out and this molecule becomes non-polar, even though it has two polar bonds. Same story here. This is chlorine, very electronegative than carbon. So each of the chlorines pull the electron clouds towards itself, and we show them by this arrow. But since the pull is equal on all the four sides, the effect cancels out. So this molecule overall also becomes polar. The overall effect is like non-polar, sorry. So carbon dioxide non-polar, carbon tetrachloride non-polar. But on the other hand, look at this, HCl. Now here, chlorine is more electronegative than hydrogen. So we see the electrons are pulled by the chlorine. That side, it's an unequal sharing of electron. This is a polar bond. Hydrogen, less electronegative. Chlorine, more electronegative. So a dipole is induced. So this becomes a polar, overall a polar molecule. Okay, so that's one thing. Now on the other hand, anytime you have, now keep this in mind, anytime there are lone pairs on the central atom, then overall molecule will be polar molecule. So you see here oxygen, dipole, oxygen and hydrogen less electronegative, oxygen more electronegative, oxygen pulls the electron clouds towards itself, oxygen has lone pairs on it. So what is happening when the dipole comes, that means that on both the sides it's a polar bond. Fine, we would expect it to cancel out, which is fine, but there is a lone pair. Lone pair means electrons just by themselves. So these electrons are free and they're negatively charged. So there's overall there is a polarity in this molecule, even though it's kind of like they should be canceling out, but because there is always lone pair on the central atom, that makes it somewhat unsymmetrical. So that unsymmetrical, if the molecule is unsymmetrical, polar. So this is a polar molecule. Okay, so more electronegative end. Now same is the case with ammonia NH3. So what is happening with ammonia? Ammonia also has the lone pair on the central atom. Nitrogen, hydrogen, individual bonds are polar. And yeah, we would expect them to cancel each other out. But there is a lone pair on the central atom. That's the electrons, right? The electrons that are negatively charged in the center, and it's unsymmetrical. So that causes it to be like polar. The more negative end is towards that side. So that's the polar molecule. And now we're going to stop here now and start doing the questions. So now let me just move this away because, all right. All right, so let's look at this now. So we have oxygen. So we looked at that fluorine is less electronegative. More electronegative than carbon. Fluorine is more electronegative than sulfur. Okay, and that's one piece. But in the same time, we see fluorine makes only one bond, and sulfur makes 2, 4, and 6 bond. Based on the table I showed you, bonds are always going to take the priority. How many bonds can a molecule in an atom make? So that's always takes priority. Okay, the number of bonds that an individual atom can make. So which one is going to be the central atom? Based on this, sulfur is the central atom, is in the central. Okay, let me just move this a little bit here because I don't want this to be cut. All right, here we go. All right, and this piece also should come here. Okay. So we have, just put it here. just put it here, times 1, and this is times 2. All right. So total is total. We have to keep is, so now we have to place sulfur in the middle. Then what will you do next? First, you're going to connect sulfur with, let's do this here, sulfur in the middle, and then fluorines on the side. And let's just put them right here at this point, and we can always shape them. All right, now we are going to connect them with a single bond. So first place this, first identify the central atom, and then you make a placement and connect them with a single bond. So we had a total of 20 electrons. 20 electrons. Okay, 20 electrons, and out of that we have used 1, 2, 3, and 4, minus 4 electrons, and we are left with remaining 16 electrons. So what do we do with the remaining 16? So these 4 electrons, I'm going to put here, used in single bonds, and these single bonds are 2 single bonds, and 16 electrons we are going to use to fill the octet. Okay, of outer atoms first. Outer atoms. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12 electrons have been used. Okay, so 12 electrons got used, and we are left with 16 minus 12, 4 more electrons left. So these leftover electrons, where are they going to go? They go on the central atom. Okay, now right here, 2, 3, 4. Okay, now you can calculate it. So you see 1, 2, let me do this here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19, 20. All 20 electrons have been accounted for. Okay, so if you look at now the octet, so octet is 1, 2, 3, 4, 5, 6, 7, and 8. 8 electrons for this fluorine. This fluorine has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons this one has, and then we have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons on sulfur. But keep this in mind that sulfur can follow the octet, but sulfur can also defy the octet. So it's like it's flexible. Okay, so when sulfur is making 2 bonds, it's following the octet, and which is fine, although it's combining with fluorine, which is more electronegative. But if sulfur is going to form 4 and 6 bond, in that cases it defies the octet. Okay, if it was to make 4 and 6 bonds. All right, so that's the shape of this molecule. Okay, next let's look at the shape of nitrate ion. You're going to do the rest yourself, the other questions. Okay, now same story here. You're going to first rule is that calculate the total valence electrons. So you have what? 1 nitrogen, you have 3 oxygens. Okay, 1 nitrogen is what? Nitrogen is in group 5A, and oxygen is in group 6A, and then there is a charge of electron. 1 electron is extra, so that is a charge. Okay, so that's coming from the charge, and we are going to account for that. So nitrogen 5 electrons, oxygen 6 electrons, right? And so what do you get here? Nitrogen 5 electrons. So 5 electrons coming from nitrogen, 6 3s are 18 electrons coming from oxygen, plus 1 more electron coming from the charge. So how much do you get here? So you have 24 electrons. So that's the total valence. Okay, so that's one piece. Now, next thing is that's one. Next thing is, which should be the central atom? Should it be the should it be nitrogen or oxygen? So remember that nitrogen can make 3 bonds, okay, but oxygen can make 2 bonds. So remember, the bonds always take a precedence. So in this case, nitrogen has to be put in the center. Okay, so that piece. Next is we are going to now connect, put nitrogen in the middle and put 1 oxygen here, another oxygen here, and another oxygen here. And now what are you doing? You're going to connect it with a single bond. 1, 2, 3, 4, 5, 6. Okay, so you have used 1, 2, 3, 4, 5, 6 electrons. Okay, so 24 electrons minus 6 electrons. Okay, so what do you get? 24 minus 6 is 18 electrons are left. So these 6 electrons got used in the single bond formation. Now, what are you going to do with the leftover 18 electrons? You're going to put them on the outer atom first. Outer atoms to fill their octet. If they follow the octet, it's not like hydrogen doesn't follow the octet, so don't do that. Okay, so here is the oxygen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So all the 18 electrons got used up, okay? Now, here we are, let me just put this here, outer atom. Okay, now, anytime there's something I did not do here, which I should have, you should always check. Here also, I'm going to come back to this again later, but let's do this. So always you check. So fine, you used all the 18 electrons, and then the other 6. So how many total? 24. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Octet is met, which is a good thing. 1, 2, 3, 4, 5, 6, 7, 8. Octet is met, which is fine. 1, 2, 3, 4, 5, 6, 7, 8. Octet is met. So this is also good. So these octets are met for oxygens, but nitrogen 1, 2, 3, 4, 5, 6. So nitrogen is obviously not happy, okay? Because its octet is not met. So what will we do? We are going to, because of that, we are going to do the rearrangement. So there are a few things you are also have to see. So rearrangement here. So you are checking number 1. You check for the octet. So oxygens, all the 3 oxygens, it is met, but 1 nitrogen is not met. Okay, it's not met. So I'll just put it here, is not, 1 nitrogen is not met. Okay, so nitrogen is obviously unhappy. Second thing is the need to make bonds. That also we have to check. The need to make the bonds. So is the need to, nitrogen wants to make 3 bonds, and that's fine. Nitrogen is making 3 bonds. Oxygen wants to make 2 bonds, but oxygen, none of these oxygens is making the 2 bonds. So oxygen is unhappy. So that why rearrangement happens. And rearrangement, what happens in the rearrangement? In rearrangement, the lone pair from oxygen is used to make double bonds. Okay. Okay, now there is also a concept of formal charge, which we are not doing here, but that you should just know that by the formal charge, we can verify the structure of this molecule. Okay, many, it's not all the time. So formal charge. So in this case, nitrogen. So we are nitrogen. So so either you make the bonds or you defy the octet. Or so here, what's going to happen? Let's just make this again. So nitrogen Here is the story with oxygen, oxygen, and oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. And 19, 20, 21, 22, 23, 24. Okay, so here is the story of nitrogen. And we have, in this case, we bring it here. Okay, so what do you have here now? So double bonded with nitrogen, oxygen, these lone pairs spread out. Okay, remember, VSEPR, valence, shell, electron, pair, repulsion. So this means that the lone pairs, they do not like the bonded atoms. So what do? They spread out. They push the bonded atoms on one side, or the double bonds, or the, so even the single bonds on one side, and themselves they occupy a very free space so that they can move freely. So nitrogen gets, this is the way, oxygen here and another oxygen here. And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Now here we have this story. In this case, the problem is, where is the charge? One of the oxygens will have to bear the charge. So where does the charge? The charge begins to, actually the charge rotates. Okay. So charge rotates. So one way of showing it like this is the charge rotates between the two oxygens. That's one thing. Okay. Now, okay, so here's something you have to keep this in mind, that internally the electrons, they talk to each other. Okay, so what happens now, they have to share the charges and they have to share the double bond. So at one point of time, this nitrogen is forming a double bond with the other oxygen, and the charge is in between those two oxygens. At the same time, at one point, then this oxygen, let's move this away. So this oxygen comes on the top, and it gets back and this one gets to keep the double bond, and the lone pairs, are put back. So what happens is, at one point, this comes here. One second. This comes here. And when that happens, this is pushed back. Okay, so that's how we get the double bond broken up between the nitrogen and oxygen. So if we put A, B, C, that's just labeling them. Okay, so at one point, A will hold the double bond. At another point, B will hold a single bond, and the C will also hold a single bond. But so here, negative. Now, again, same story. This needs to form a double bond. So now this bond breaks. So now this is what is going to happen. Now we will see, okay, here, nitrogen, single bond, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and double bond. 1, 2, 3, 4. Okay, and now the charge is here in between the two. Okay, so you see the charge was initially between B and C, then the charge goes between A and B, and then it comes between C and A. So the charge moves in all these different places. Let me label this again. So this was A oxygen, B oxygen, and C oxygen. Okay, so the other way of showing this is actually, these are the resonating structures. So another way of showing is you can show any one of the structures, it doesn't matter, but you can show it as nitrogen, oxygen, 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 double bond, right? 1, 2, 3, 4, 5, 6. And this structures has been verified by the, like that. just to show that the charge rotates between the three. Okay, so you can show it like that. And these are called the this is resonance, and these are the resonating structures. Resonating structures, all of them. So on the exam, you have to show all resonating structures on the exam. On tests. Okay, like as working. This is the working for the Lewis structures. Okay, so like I said, valence shell electron pair repulsion causes the double bond to be shifted, you know, on one side, a single bond on one side, and the lone pairs on the one side. All right, so that's the thing with these charges, with these structures. And you know, the need, at least oxygen wants to make two bonds. So with this rearrangement, each oxygen gets a fair turn to make the two bonds. Okay, all right, and so, and then nitrogen also gets its octet, if you look at it. See that? So 1, 2, 3, 4, 5, 6, 7, 8. Each of the oxygens have their octets. Nitrogen also have the octet. Nitrogen is making 4 bonds, and that's, you know, it should be making 3 bonds, but it's fine. And nitrogen can make 4 bonds also. Okay, and then oxygens, you know, they only make 2 bonds. Okay, so that finishes this part. Now we're going to look at the next concept of polarity. So hold on. Okay, so now we are looking at the electronegativity concept. So here the question is 63, 65, and 67. They relate to the electronegativity and bond polarity. So the question is, the first one, arrange these atoms in the increasing order of electronegativity. And here you will be using the periodic table. Okay, so let's look at this. Okay, so increasing order of the electronegativity. So what was the question? So one thing is, here is, it's like this, I have. Okay, so this is one piece. Let's see. And then the second thing is that there is a trend in the periodic table in your handout, the increasing ionization energy. Increasing ionization energy refers to electronegativity also. Okay, so electronegativity increases. Increasing ionization energy means that the electronegativity increases when you move in the periodic table from left to right. But when you move from top down, the electronegativity goes down, it decreases. Okay, so the question is that describe the trends in the electronegativity as it increases or decreases when you move, increasing of, so which one did I take? Lithium, sodium, potassium. So lithium, sodium, potassium are in group 1A. Okay, so when these guys, when they are in the group 1A in the periodic table, they move from it goes down. So let's look at this now. So lithium, sodium, potassium. So let me just put this here. Increases and decreases. So electronegativity goes down when you move from top to bottom. Okay, and when you move from left to right, the electronegativity increases. So all you need to do is you need to place them in the periodic table. So lithium is on the top, beryllium, lithium, sodium is next, and potassium is after that. So we see that the electronegativity is decreasing. So lithium has a higher electronegativity than sodium. Sodium has a higher electronegativity than potassium. Okay, so that is the increased electronegativity. Next is sodium, chlorine, and phosphorus. So let's look at the periodic table and look at the sodium, chlorine, and phosphorus. Where are they located? So if you can just, I don't know how to flip it, but here's the sodium in group 3A, and then sodium, and then comes next is phosphorus, and then is chlorine. So chlorine is highest. Okay, so just do this. So here sodium, so this is in the same period. So we see that sodium has the lowest, then comes phosphorus, and then comes chlorine. Okay, so that's the answer to this one. So that's the trend in the periodic table. Next, we have to look at the bonds, and we're going to tell whether these bonds are polar, ionic, and net ionic. So here you're going to use the electronegativity values that are given in the period in that table. Okay, let's look at that. So in the handout, we have the electronegativity values of these elements. Sorry, where is it? Just give me 1 minute here. Okay, these are the electronegativity values. So the question is that for which one did we do? SIBR, for example. So silicon is 1.8. Silicon is the electronegative value for silicon is 1.8, and that for bromine is 2.8. Okay, so 2.8 minus 1.8 is 1.0. So 1.0, where does it come? It comes in between 0.4 and 1.8, right? So it comes in between, and that makes it a polar covalent bond, and you need to show it with these. So let's do this here. So silicon is, so I'm going to put bromine is higher. So bromine and silicon. Silicon electronegativity value 1.8, bromine 2.8. Okay, so delta En, change in the electronegativity, right? The change in the electronegativity is 1.0. And when we see that 1.0 falls under the polar covalent category. So polar covalent, and anything that is polar covalent means there's unequal distribution of electron, which means bromine being more electronegative will have a delta negative charge, and silicon being more electropositive will have the, or less electronegative value will have the delta positive charge. Okay, so that's one thing. Now let's look for nitrogen and fluorine, and yeah, and there's this an arrow. So arrow is going to be towards bromine. Next is nitrogen and phosphorus. Let's look at nitrogen, the value for nitrogen. Nitrogen is 3.0 and phosphorus is 2.1. So 3.0 minus 2.1 is what? 0.9. So 0.9 falls again 0.4 to 1.8 in this. So it is a polar covalent bond. Nitrogen and phosphorus. So here nitrogen, let's just do it with a different pen. And nitrogen and phosphorus. Okay, I forgot now. Give me 1 minute. Nitrogen 3.0, phosphorus 2.1. 2.1 and 3.0. So this is 0.9, and that falls between the polar covalent. So that polar covalent means that phosphorus has, no, sorry, nitrogen has a delta negative and phosphorus has a delta positive. Right? Lesser electronegativity. So which side is the polarity towards? It's towards nitrogen. That's the net polarity, is towards nitrogen. Okay, let's look at iodine and iodine. Iodine, the value for iodine is 2.5. Okay, so 2.5 and minus 2.5. So that is going to be like 0. So where does it go? Non-polar covalent. The electrons are equally shared. So iodine, let's do this way. Iodine 2.5, and the other iodine also is 2.5. So this becomes 0. Okay, and that is a non-polar covalent bond. So that means no net polarity, right? No charge, no delta negative or positive charge. Okay, next is they're saying again dipole with the arrow and delta. So you have to make these charges again. So here nitrogen and fluorine. Nitrogen and fluorine. Nitrogen is 3.0 and fluorine is 4.0. So this makes it 1. The difference in the electronegativity is 1, and that is a polar covalent bond. So fluorine, nitrogen 3.0. Okay. So let's do this here. Nitrogen is 3.0 and fluorine is 4.0. Fluorine is equal to 4.0 and nitrogen is equal to 3.0, and this becomes 1.0. Okay, and that is a polar bond. So nitrogen will have a delta positive, although nitrogen is delta negative, but it's always in comparison. It's always because fluorine is more electronegative than nitrogen. So overall polarity is towards fluorine. So this is a polar covalent bond. Okay. Next comes carbon and oxygen. Same story. You have oxygen 3.5, carbon 2.5. Okay. Oxygen 3.5, carbon 2.5. So here 3.5 minus 2.5, again, same thing. Oxygen 3.5 and carbon 2.5. So this becomes 1.0, and that is again a polar bond, and that means oxygen delta negative, carbon delta positive, and the polarity is towards, the net polarity is towards oxygen. All right. So next we are going to look at the shapes in the next video. Okay. I'm going to stop now.